Okay, so you know that we've seen a few martingales and we've seen an application of what they can do for us. We're going to have a look at their analytical properties, and they have very nice analytical properties. In particular, we're going to show a convergence theorem that if says that if martingales are uniformly in L2, then they always converge in L2. So that's going to be extremely helpful, and all the rest of the course, in particular in constructing calculus. And you know that if you have a lot of converging sequences, doing calculus is much simpler. So in proving the theorem about L2 convergence of martingales, well, we're going to need to show that we have Cauchy sequences, so we need to control increments of martingales. And what's going to allow us to do that is a technical tool called a maximal inequality. So we're going to show that the worst case scenario in terms of how large increments can be is actually fairly small. So the probability of having large increments in a martingale gets quite low as you ask for that increment to be particularly large. So that's a very important technical tool from an analysis point of view, being able to control the largest possible increments of a sequence. From a more applied point of view, what is that telling us? It's telling us that when we have a martingale and we look at an extreme event, so we look at gigantic variations or just in absolute value, the process getting particularly large, this is unlikely to happen, right? Martingales are good from a modeling point of view to model situations that are reasonably close to equilibrium, that are reasonably far away from crisis. They don't look at extreme events that are particularly likely. I mean, they cannot model extreme events that are particularly likely because, as we are about to prove in this section, the probability of an extreme event is low. So how do we formalize what I just said? Well, okay, we're going to be in the context of non-negative submartingales. So typically they arise by taking the absolute value of a genuine martingale or taking the square of a genuine martingale. So that makes them non-negative. You might lose the martingale property, but you will remain a submartingale. That's a consequence of Jensen inequality. Now, this idea of extreme events is going to be modeled by using a mathematical tool called a maximal function, or in this case, because we're in discrete time, a maximal sequence. And that's defined right here. It is just taking the maximum value. So at a time n, it's looking at the maximum value that the sum martingale took at all the times before 2n. So the maximum for k between 0 and n. So this sort of object where you have something that evolves, say, over time, or that's indexed by a parameter, and you look at an object that is the maximum or the supremum of that parameter. So taking a maximal function of a certain function, it's a very common tool in mathematical analysis. And the idea is that if you can control the maximum, well, then you have very nice uniform estimates on whatever it is you're looking at. And uniform estimates are particularly helpful in proving convergence and proving a whole range of analysis property, because uniformity is what we need, for instance, to exchange limits. So if we can control mn star, that's going to give us very good control on the mn's. Now, Doobe's maximal inequality is exactly that. It tells us how to control mn star. So same context, you have a non-negative submartingale, you form its maximal sequence, and what Doob maximal inequality is telling you is that for every time and for every parameter alpha that describe how large you would like your extreme event to be, you can describe the probability of the maximal function getting above that threshold. So the probability that the extreme event was particularly large, let's say whatever, greater than 100, you have the alpha here. So this is basically telling you that this will decay like some constant if your martingale is uniformly in L1 or uniformly in L2 divided by alpha. So typically speaking, the probability of being above 100 is going to be roughly 1%. So that's going to be very helpful both in applied situation, in measuring the size of extreme events when you know that they are correctly modeled by martingales, and in the development of stochastic analysis and controlling all sort of things uniformly thanks to those inequalities. Now, I've been describing the left-hand side and the very far right-hand side here. There's a little something in between here, which is a slightly refined estimate that we will get from the proof. And getting this slightly refined estimate from the proof is very nifty. It's going to help us prove bound on the L2 norm, in particular of the maximal function later on, very neatly, because we have that extra little bit of information in the proof of the inequality. So let us prove this maximal inequality. Now, to do that, I'm going to give myself two natural numbers, n and m, and I'm first gonna prove the following little claim. I'm going to show that for every a in Fm, the expectation of mm indicator function of a is always smaller than the expectation of mn indicator function of a. So as time passes, the expectation increases. Now let's see how that goes. So I want to compute the expectation of mm times the indicator function of a, that is the integral over a of mm, but mm is certainly smaller than the conditional expectation of mn given fm. That's because n is above m and mn is a submartingale. Right. Now, okay, by definition of what being a conditional expectation is and the fact that a is in fm, I have that this is the same as the integral over a of mn, which is the expectation of the indicator function of a times mn. Right, so that proves my little claim here. That's going to be very helpful in the rest of the proof. Now, the next thing I'm going to do, that was step one if you want. The next thing I want to do is introduce a stopping time. So I'm going to define tau, going from omega to n union infinity in the following way. It's going to be the minimum of those n for which mn of omega is greater than alpha, right? I'm looking at the first time at which the martingale has gone above the threshold that I'm interested in. But of course, maybe it never goes above that threshold, so I'm going to put it at infinity if mn of omega is below alpha for every n, right, which is the opposite situation. Okay, so this is the first time at which we go above the threshold. Obviously, if that stopping time is finite, then m star n for n above that stopping time will be above alpha. Now, I'm claiming that this is a stopping time. How do we see that? Well, what is the set where tau is smaller than n? For any n, a natural number. If some mn before n as some mj before n has gone above alpha, that means one of the fj has gone above alpha. So this is really the union of all the sets where mj has gone above alpha, right? Having the stopping time, having this stopping time happen before n means that the threshold has been reached for some j between 0 and n. So this is the union, a finite union of sets, and these sets are in Fn because, well, each one of them is in Mj. So Mj greater than alpha, that is Mj minus 1 of the closed set alpha to infinity. Therefore, it's in Fj because Mj is Fj measurable, and Fj is in Fn. So what I have here is a finite unions of things in Fn, therefore it's in Fn. Because Fn is a sigma algebra, and that tells me that tau is a stopping time. So let's use this stopping time. I want to compute alpha times the probability that the maximal sequence is greater than alpha. Now, having mn star greater than alpha is really the same thing as having the stopping time being below n. Right? The stopping time being below n means that there is some j between 0 and n at which mj is greater or equal than alpha, so the maximum of the mj is greater or equal than alpha. So this is just a way of rewriting using a stopping time this condition mn star greater or equal to alpha. Now, my stopping time being smaller or equal to n, I can rewrite that in terms of expectation. I can use the linearity of the expectation, and this is just another expression for the exact same thing. Now, at the point of time tau, at the stopping time, the maximal process, the maximal sequence has gone above alpha. So this here is certainly smaller than the expectation of m of tau times this indicator function, because m of tau is always greater or equal than alpha. And I have a monotonicity property of just standard expectation. Now, tau being smaller than n, well, this can happen in various ways. You can write that as a sum from j equal 0 to n of the expectation of m of tau times the indicator function of tau being equal to j, right? So if tau is smaller or equal to n, it means it's some number between 0 and n, and then I use linearity of the expectation. Now, if tau is equal to j, then this here is exactly the expectation of mj whenever tau is j, all right? Now, what have we seen? So tau being equal to j, that's an element of fj. J is smaller than n, and so by the claim, this is smaller than the sum from j equals 0 to n of the expectation of mn times the indicator function of tau being equal to j, right? The expectation from here to here, I use the fact that the expectation increases as time increases when tested on sets in fj. That was the purpose of that claim. And now the point is that here, both this part and that part were varying in j. Now this is the only part that varies in j, so I can bring the sum back inside and realize that this is nothing but the expectation of mn times the indicator function of tau being smaller than n, all right? Because the sum of this indicator function of tau equal to j is going to be 1 if tau is smaller or equal to n and 0 is otherwise. Now, what is that? Well, tau being smaller than n is exactly the same thing as mn star being smaller than alpha. So this is just a rewriting for the expectation of mn times the indicator function of mn star being greater than alpha. And that is this technical middle part in the chain of inequalities that I'm trying to prove. And then the last part is obvious. This is smaller than the expectation of mn. That's by the monotonicity of the integral. This is smaller or equal to that because the indicator function is just 0 or 1. And I should not have done that this way. And that concludes the proof of Doobe's maximal inequality. Now, it's worth pausing here and having a little remark for those of you who might have done some Fourier analysis or some geometric measure theory. You might have seen the weak type 1-1 estimate for the highly little maximal function. That's a fundamental result in harmonic analysis, in differentiation theory, as part of geometric measure theory in particular. Now, this geometric result is extremely important and not particularly easy to prove by purely analytic tools. Now, we'll see in the next video that, not the next one, but maybe 2 videos down from here, that the dyadic martingale is such that its maximal sequence is the Hardy-Tude maximal function. So if you know about Hardy-Tude maximal function, what you are seeing here, so this Doob maximal inequality is a different proof of the weak type 1-1 property, and it's a proof that is more general, that works for general martingale, and that provides you with the best constant. So if you come from analysis, if you've done a bit more analysis, especially Fourier or harmonic analysis, this result of Doob you might find fascinating. I certainly do. This is a very nifty proof using martingale theory that provides optimal analytic result. And in fact, that's a very common fact that using probability to answer analysis question gives you optimal inequalities. So we can control the size of the maximal sequence associated with a non-negative submartingale. There's a useful little corollary of that which tells you that you can actually control the supremum over all time of the martingale. That's a direct consequence of the inequality we've just proven, because you apply the monotone convergence theorem, and the limit as n goes to infinity of your mn star will be exactly this supremum. So you apply the monotone convergence theorem, the left hand side converges to this expression, alpha times the probability that the supremum of the mk is greater or equal than alpha. And on the right hand side, well, you had the expectation of mn, and you want to take a limit as n goes to infinity. You can certainly control this by the supremum over all these expectations. So what you get is that if you have a non-negative submartingale that's uniformly in L1, so this is a constant, then you can control that probability that the supremum of the mk is large, is greater than alpha, as 1 upon alpha times this constant, which is the supremum of the L1 norm. That's a direct consequence of Doob inequality that we're going to use quite often in the rest of the course. Now, the next thing we're going to prove are the Dupes Lp inequalities. So we've proven something about the probability of the maximal sequence being large, and we're going to use that to say that the norm, the L2 norm in particular, of the maximal sequence cannot be too large. Now, I've expressed this result not just for p equal 2, which is the value of p for which we're going to use it most of the time, but for general p, because the proof is the same. And for those of you who've done a bit of analysis in LP spaces, this is interesting to see that, and to see in particular how the constant depends on p and how it explodes as p approaches 1. So we don't get an L1 control of the maximal sequence. In fact, what we get is a weak type 1-1 inequality, which is precisely the Dupes maximal inequality we've proven before. But that's a little aside for those of you who've done more analysis. For all of us in this course, this inequality is going to be used mostly for p equal 2. And then for p equal 2, it's telling us that when you take the maximal sequence, so you really just take the worst possible value in the interval of time 0 to n of your martingale, you're still gonna be in L2. Maybe not with the same L2 norm as the martingale itself, but 2 divided by 2 minus 1 is 2, but at most double that, right? So the L2 norm, this variance of the maximal sequence, so the variance of the extreme version of our process, is at most twice as big as the process itself. That's a very tight control on the size of the maximal sequence. That's going to be particularly helpful. And once again, it shows you from an applied point of view that you're looking at things that are very well behaved, that are very far away from crisis, right? The extreme version are not much bigger than the non-extreme version. That's the moral of this inequality. Now, this follows reasonably directly, these inequalities we want to show here about the size of Mn star follow fairly directly from the control of the probability of Mn star being large that we've seen before, thanks to the specific form of the maximal inequality we've proven. Indeed, the theorem will be a direct consequence of the lemma just below it. So what is the lemma telling us? Nothing to do with martingales. It's a general fact about non-negative random variables. If you have two non-negative random variables, and one of them is in LP for some p. You can take p equal 2 in all of that if you want, if you don't want to deal with more general LP spaces. And you have an estimate of alpha times the probability of x being greater than alpha. And it's controlled by this particular kind of quantity. So notice that this statement is exactly meant to apply the maximal inequality we've proven with x equal mn star and y equal mn, right? That's exactly what we're going to apply the lemma with. So mn will be in L2 and or in LP in the statement of our theorem, and we don't know if mn star is going to be in L2, but we're going to deduce that it is. And indeed, what we derive is exactly the statement of theorem 2.1.4, namely that the mn star in LP norm is controlled up to this constant p divided by p minus 1 by the LP norm of y, which is going to be our mn. So if we prove this lemma, which is a general fact about non-negative random variables, we will satisfy the assumption of the lemma using the Doobe's maximal inequality that we've proven before, and we will derive the Dupes Lp inequalities that we're trying to prove. Okay, so in proving the theorem, we're first going to assume that the variable x is also in Lp. Right, and we'll remove this assumption in a second step of the proof. So assuming it's in Lp, I want to compute the Lp norm of this, right? That's what I'm trying to control. And the Lp norm of that is given by the integral from 0 to infinity of p lambda p minus 1 times the probability that x is greater than lambda. That's the way you relate the Lp norm of a random variable to this kind of probability of the variable being large. If you're like me and you have trouble remembering this, I don't know why I've always had trouble remembering that, what I tend to do is try to reprove it. So start with the right hand side, or your best guess for it. Maybe you mess up the p and the p minus 1 to start with, as I do quite regularly, and you wonder what that is. So what is that? So x being greater than lambda, I can rewrite that as the expectation of the indicator function of that set. So this is the integral of dp on the set where x is greater than lambda. And then I exchange the two integral, and I know that my lambda has to be smaller than x. So this tells me that I'm integrating over omega the integral from 0 to x of omega, because my lambda is at most x of p lambda p minus 1, d lambda dp omega, and then okay, this is the derivative of lambda to the p. So what I'm getting is the integral of omega of x omega to the p dp omega, which is equal to the Lp norm of x to the x. So I have to redo this computation every time. I think I've done it probably 100 times in my life, and I still don't remember this formula. But it's easy to reprove. All right. Now, once we have this, let's start using the assumptions of our theorem. And the assumption of our theorem tells us that lambda tells us something about lambda times this. So let's put a p minus 2 here and get the lambda in front. And now what we know is that lambda times the probability of x being greater than lambda, that's controlled by the expectation of y times the indicator function of the set where x is greater or equal to lambda. The lambda, very good. And then you just rewrite that. It's actually similar to that proof I did here in the little box. You're integrating over the set where x is greater than lambda, y of omega dp omega. Okay, fine. Let's exchange those two integral, and let's just integrate over all of omega, but now y of omega, but now I'm integrating in lambda only up to x, and I'm integrating p lambda p minus 2 d lambda. And now that's not quite the derivative of lambda to the p minus 1, but almost up to a constant. So I get p, sorry, this is up to x of omega, and I get p divided by p minus 1, that's where the constant comes from, times x of omega to the power p minus 1, dp of omega. All right. So that's exactly p divided by p minus 1 times the expectation of y times x to the p minus 1. Now I'm going to apply Euler inequality. Let me remind you what it is here. Is the generalization of Cauchy-Schwarz inequality to LP. If you haven't seen that, don't worry about it. We will deal mostly with P equal 2 in this course, and therefore we will only use Cauchy-Schwarz inequality. But for those of you who know LP spaces a bit more generally, why not do it in this way? So Euler inequality tells me that whenever I have a product of two variables, x and y, the expectation of x times y, absolute value, is controlled by the LP norm of x times the LP prime norm of y, where p prime is the solution of 1 upon p prime plus 1 upon p equal to 1. So notice that 2 prime is 2, and you get that the integral of a product is controlled by the product of the L2 norm, and that's Cauchy-Schwarz inequality. All right, so let's apply it here to this product, y times x p minus y, because I want something in terms of the LP norm of y. So applying Euler gets me to, or applying, if you'd rather, just Cauchy-Schwarz, that gives me the LP norm of y times the LP prime norms of x p minus 1. Now, what is p prime in terms of p? So, well, 1 upon p prime is 1 minus 1 upon p, so that's p minus 1 divided by p. So what I have here is p minus 1, LP norm of y, and then I have the integral of omega of x to the x omega to the power p minus 1 raised to the power p prime, which is p divided by p minus 1. And then I raise all of that to the power 1 upon p prime, which is p minus 1 divided by p. So what I have here really is p divided by p minus 1, LP norm of y, and then the LP norm of x raised to the power p minus 1. So what have we proven? We've proven that the LP norm of x raised to the power p is smaller than p upon p minus 1, LP norm of y times LP norm of x raised to the power p minus 1, and you divide by that on both sides, and you get the inequality we wanted to get. So we've proven our result, right? Except we've only proven it under the extra assumption that x was in LP to start with, right? Such that we could start computing the LP norm of x using probability of x being greater than lambda, integrating over lambda. Now, that is not a big limitation, as it's going to be the case throughout this course. Very often we add some extra qualitative assumption on our random variables in order to prove a theorem, and then we use an approximation argument to get rid of the extra assumption at the end. Now, how do we get rid of this extra assumption that x is in LP here? We approximate x by elements that are even in a L infinity. And then we're going to use a monotone convergence argument. So in order to remove the assumption that x, so for general x, we define xn, that's going to be the minimum of, at the point omega, of x of omega and n for all omega and for all n. Now xn is in L infinity, and therefore it is in LP, because L infinity is even smaller than LP. Right, so we just have that the LP norm by step 1, that the LP norm of x, let's not raise that to any power, is smaller or equal to p divided by p minus 1 times the LP norm of y, and that is for all n in n. Now xn increases to x for every omega, right? Because it's defined as the minimum of x of omega and n. And so by monotone convergence, xn, well, that's also true, is xn to the p, and so you're going to be able to take the integrals of that thanks to the monotone convergence theorem. By monotone convergence, we get that the norm of x in LP has to be smaller than the lim inf of the xn in LP, and this is smaller than p divided by p minus 1 as n goes to infinity. And that concludes the proof of the Dupes Lp inequality theorem.